So in path of charge particle, this is case 4. If charge particle is moving perpendicular to magnetic field. Not perpendicular, it's moving at an angle theta to magnetic. So in path of charge particle, case 4, if charge particle is moving at an angle theta to magnetic field. So if this is magnetic field, this is the direction of magnetic field. This is magnetic field B. This is your charge particle Q. This particle is moving with a velocity V at an angle theta to magnetic field. Now to decide the path of charge particle in this particular case, you can resolve this velocity into two parts. You can take one component, which is V cos theta. This component is parallel to magnetic field. I call this as V parallel. Then you can take another component, which is V sin theta. Another component, which is V sin theta. V sin theta is component which is perpendicular to magnetic. So magnetic force acting on charged particle. Now to decide the path of charged particle, we will solve this parallel and perpendicular component separately. Okay, Johanna, just tell me, what's the path of charged particle due to component parallel to magnetic field? This we have already did in case 1 or case 2. V parallel is component of velocity. Yes, same direction. Straight line, path would be straight line in the same direction. It's component of velocity parallel to magnetic field. And this V perpendicular is component of velocity. This is component of velocity perpendicular to magnetic field. Now to decide the exact part of the particle, we will solve this V parallel and V perpendicular separately. We will solve both V parallel and V perpendicular separately. Let's first decide path of charged particle due to V perpendicular. Path of charged particle due to V perpendicular. Do you remember? What should be the path of charged particle due to component of velocity perpendicular to magnetic field? Yeah, it would be circular. So path would be circular. So first of all, calculate. In that circular path, you're supposed to calculate the radius of the path. Along with radius of the path, you have to calculate the frequency and the time period. So I'm repeating the calculation of that case 3, where charged particle is moving perpendicular to magnetic. So first of all, let's calculate magnetic force. Now I'm repeating the case 3. Magnetic force on the charged particle. The magnetic force on the charged particle is Q. It's V perpendicular. It's B sine 90. Sine 90 is 1. So FB, magnetic force is Q. It's V perpendicular into B. That's my first equation. This is the magnetic force on the charged particle. Then to move in the circular path, this charged particle will need a centripetal force. Centripetal force required. If you remember, I'm just repeating the derivation of case 3 here. The required centripetal force is mv square by r. But instead of v, we will use v perpendicular, mv perpendicular square by r. Magnetic force will provide centripetal force. Magnetic force will provide centripetal force. So you can write that your centripetal force is equal to magnetic force. Your centripetal force is mv perpendicular square by r is, okay. Joanna, we have to decide the path of the charged particle if the velocity is at an angle theta to magnetic field. To decide the path of charged particle in this particular case, the easiest way is to divide this velocity into two components, one v parallel and another v perpendicular. You already know that the path due to this v parallel would be straight line. Path of charged particle due to this v perpendicular would be circular. Then we will combine them to get the resultant path. This is how we proceed in this particular case. First, we will decide the path due to v parallel. Then we will decide the path due to v perpendicular. And then finally, we will combine them to get the net path. Is it clear? So this is q v perpendicular into p. This square will cancel this v perpendicular. And what we get r is mv perpendicular over q. Okay, now can you tell me how to calculate the time period? So we can use the concept of velocity, that v perpendicular is distance upon time. So distance is 2 pi r divided by t1. So from here I can write that the time period is, it's 2 pi r over v perpendicular. Let's call this as equation number 4. This is equation number 3. I can substitute 3 and 4. On substituting 3 and 4, I will get that time period is, it's 2 pi r. It's 2 pi mv perpendicular by qb into v perpendicular. So v perpendicular will cancel v perpendicular. The expression of time period is, it's 2 pi m over qb. The expression of frequency is 1 by time period. So it's qb by 2 pi m. That's frequency. This is equation number 5. So the path due to the component of velocity perpendicular to magnetic field would be circular. This is the radius of the circular path. And this is the frequency and time period of circular path. Next, we will calculate the path due to v parallel component. Now, as you already know that the path due to this v parallel component would be a straight line path. Path due to v parallel will be straight line. So this v perpendicular will give circular path. This v parallel will give straight line path. The combined path due to v parallel and v perpendicular would be circular plus straight line. Okay, can you guess the combination of straight line and circular path? If a body is moving on a circular path as well as it's moving forward, so what would be the exact shape of the path? No. The combination of the circular as well as straight line path would be helical. So the combined path of the particle would be like this. This charged particle will be moving in a circular path due to perpendicular component of velocity. And along with this circular path, this charged particle is moving in forward direction. So the circular path is, the radius of the circular path is r. And the radius we have already calculated. This is mv perpendicular by qb. The next thing is you have to calculate this horizontal distance covered by the particle. This distance is known as pitch. In each circular path, the particle will move like this. It will cover a circular path and it will move forward, then it will move forward. So along with circular, it's moving in the forward direction. This distance that the particle cover is known as pitch of the path. For helical path, we already know radius. That radius is 2 pi mv perpendicular by qb. Next, we need to calculate this pitch, this horizontal distance. Now, Johanna, can you guess which component of velocity is responsible for pitch? V perpendicular or V parallel?
V parallel.
V parallel. And pitch is distance. So pitch, we can write this as pitch is horizontal distance covered in time capital. So the horizontal distance that the particle cover in time capital T is known as pitch. We can write pitch as the combination of V parallel and T. Pitch is a distance which is speed into time. So your pitch could be written as V parallel, and time period. Time period is QB by 2 pi. 2 pi m by Q. So if a particle is moving at an angle theta to magnetic field, which is obviously not 0 degree, neither it is 90 degree. So the path of charged particle would be helical. The radius of the helical path is this mv perpendicular over qb. And the time period is this 2 pi m by qp. And this is the pitch, the horizontal distance that the particle cover, which is v parallel. Next, solve this problem. So if we ask you to describe the path of charged particle, that means first of all you will mention that the path is helical. Then you will calculate the radius of path, then you will calculate the time period of the path, and then you will calculate the pitch. So while calculating radius, we are using, this is mv perpendicular by qb. Your v perpendicular is v sine 30. So it comes out to be v is 10, sine 30 is half. So your v perpendicular comes out to be 5 meter per second. Similarly, let's calculate V parallel. V parallel will be V cos 30. So your V is 10, cos 30 is root 3 by 2. That comes out to be 5 root 3 meter per second. So this is V parallel and this is V perpendicular. So your radius is mv perpendicular by qb. So it's mv perpendicular is 5. Your charge is 2 coulomb. Your magnetic field is 10 Tesla. Yes, it comes out to be m by 4. After radius, you can calculate time period, which is 2 pi m by qb. So that comes out to be 2 pi m over charge, which is 2 coulomb. Magnetic field, which is 10 Tesla. So time period comes out to be pi m by 10. After time period, you can calculate pitch, which is nothing but the product of V parallel into time period. So your V parallel is 5 root 3 into pi m by 10. So you can write your pitch as that's 5 root 3 pi by 10. So I'm cancelling this 5 and 10. So it basically comes out to be pi root 3 m by 2. Okay, after this motion of charged particle in magnetic field, the next topic is there are few devices which are based on this magnetic Lorentz force and Lorentz. So the first device is known as velocity selector. The first is velocity selector. So first of all, see what this device do. It select charged particles of a particular velocity from a beam having variable velocities. Which means, say you have a beam of charged particles, say you have a beam of proton. This proton beam have protons of almost all velocities. You have protons moving with velocity of 10 meter per second, 20 meter per second, 50 meter per second, up to 100 meter per second. I ask you to select some protons having velocity of 50 meter per second only. So from this beam having protons of every velocity, if you wish to select protons of a particular velocity like 50 meter per second, to select protons of this particular velocity, the device that you will use is velocity selector. This is the use of velocity selector basically. It can select charged particles of a particular velocity from a beam having variable velocities. Is it clear? Next, after what is velocity selector, the next thing is the principle. So the principle says that charged particles moving with velocity v is equal to E by B in a region having cross electric and magnetic field will not experience any force and gets selected. Now, what this principle means will get clear once we start the theory of this velocity selector. So I'm not explaining the meaning of this whole statement. We will do this thing while doing theory of velocity selector. After principle, the next is construction. It's a very simple setup. You just have a beam having charged particles of variable velocities. Say this is the beam. This beam have charged particles of many velocities. Charged particles of various velocities. Then there is this central region. This central region have cross electric and magnetic field. Cross electric and magnetic field means perpendicular electric and magnetic. This is electric field and this is magnetic field along z axis. Cross electric and magnetic field. So this is the electric field and this is the magnetic field. Cross electric and magnetic. And beam is moving in this direction. And beam of charged particle is moving in this direction. It's moving in this direction. This is charged particle moving in this direction with a velocity. Then there is this wall with a very small opening. This is the construction. These are the walls. Charged particles cannot penetrate this wall. Charged particle can pass through this wall only through this small opening. And the rest electric and magnetic fields are mutually perpendicular. This is beam of charged particle Q. It's moving with a velocity. This is the simple construction. This beam is coming, having charged particles of variable velocities. Then there is a region having cross electric and magnetic field. Electric field is along y-axis, magnetic field is along z-axis. And the charged particle is moving perpendicular to both. Then there is this wall. Charged particle can pass through the wall through this small opening. Now look at the theory. See, the charged particle moving in this region will experience both electric as well as magnetic field. So the charged particles will experience electric force as well as magnetic force. Due to electric and magnetic force, obviously if a force is acting on a charged particle, then its path will get deviated. So the path of charged particle will get deviated. It can move in this way. Another charged particle experience some force, its path will get deviated. Charged particle will experience some force, its path will get deviated. Once its path gets deviated, it's collide with the wall and cannot cross the wall. But charged particle of a particular velocity v, we will decide what is the value of this particular velocity. But the charged particle of this particular velocity will not experience any force. If they don't experience any force, then they will not deflect. They will rather move in a straight line. They will not deflect, they will rather move in a straight line. And they will pass through this wall and get selected. So the charged particles, those charged particles which experience no net force will pass through the wall without any deflection and get selected. The rest of the charged particle will experience some force, and due to this force, they get deflected and collides with the wall of container, these walls, and they will not get selected. Now the thing is, which particular velocity, yeah, I'm coming to it, Joanna. How they will not experience any force, I'm coming to it. Now the thing is, how they will not experience any force, which particular velocity will not experience. For this thing, say this is a positively charged particle. This charged particle is in a region of electric as well as magnetic field. So the electric force experienced by the charged particle, electric force on charged particle, Fe. The electric force on the charged particle is this is QE. And this electric force will act in the direction of field. So the field is acting upwards, the force will act upwards. So this is the direction of force along J graph. That's my first equation. Electric field exerts force on positive charged particle in the direction of field. So we will simply experience force in the y axis. Now the magnetic force on the charged particle. Magnetic force on charged particle. The magnetic force on the charged particle is Fb, which is basically Q V cross. This is the magnetic force on the charged particle, which is Q V cross. V and D are perpendicular to each other. The angle between them is 90 degrees. So if I open this cross product, this is QVB sine 90. So it's very clear. V is along x-axis, B is along z-axis, so the angle is 90. Okay, Johanna, just apply right-hand thumb rule and decide the direction of magnetic force. V is along x-axis, B is z-axis, out of the plane of board. It's out of the plane of the board. Can you decide the direction of magnetic force? Apply right-hand thumb rule to get the direction of magnetic force. Your velocity is along x-axis and your magnetic force is out of the plane. Yeah, very good. If you apply right-hand thumb rule, it will go downwards. So can I write this as minus of j cap? That's second equation. So now I'm writing here. Particle will get selected. Particle will get selected if net force, which is sum of magnetic force as well as electric force, is equal to 0. See, your magnetic force is QVB minus J cap. Your electric force is QEJ cap is equal to 0. You can take this thing to the right hand side. So you'll be left with QEJ cap is QVBJ cap. Since both the forces are acting in opposite directions, so for a particular value of velocity, they could be equal. Means magnetic and electric forces are equal to each other. This j cap will cancel this j cap, this q will cancel this q, and you will see that E by B is equal to V. So if a charged particle is moving with this velocity, then electric and magnetic force would be equal or in opposite directions, so that they can cancel out each other. The net force over the charged particle would be 0, and so it will pass in a straight line. That's why I wrote here this moving with the velocity E by B will move in straight line. So that was about velocity selector. Okay, after velocity selector, solve this question. This is the direction of velocity of a negatively charged particle. This negatively charged particle is moving with a velocity v to the right hand side. This is the direction of the electric field. Predict direction of magnetic field. Magnetic field so that net force on particle is 0. So that net force on charged particle is 0. Okay, I'm telling you the step. You perform those steps on yourself. First, get the direction of electric force. First of all, get the direction of electric force. So what's the direction of electric force here? Yes, Joanna, what is the direction of electric force? Not along x-axis. The direction of electric force is opposite to that of electric field. Your electric field is upwards. Your charged particle is negative. The negative charged particle experience force in the direction opposite to that of field. This is the direction of electric force. On negatively charged particle, on negative charged particle, direction is opposite to field. So if electric field is upwards, the electric force is down. Okay. The second force that can act on this charged particle should be in upwards direction, then only the net force would be 0. So now you know the direction of magnetic force. The magnetic force, so this is along negative y-axis. Your magnetic force should be along positive y-axis. Joanna, is it clear up to this point?
Yes, sir.
Now you have to predict the direction of magnetic field so that your magnetic force is upwards. So this is sort of reverse calculation. If you know the direction of velocity and direction of magnetic field, then using right hand thumb rule, you can get the direction of magnetic force. This sort of reverse calculation. You know the direction of magnetic force. You know the direction of velocity. You have to predict the direction of magnetic field. That thing you can do in this way. This is the direction of velocity. This is the direction of force, y, positive y-axis. You have to predict the direction of magnetic field. For this, just remember one small trick, that magnetic field is perpendicular to both velocity as well as magnetic force. Okay, how you decide negative z-axis, Joanna? By hit and trial method?
Sir, I used right hand thumb rule, but like I
Assume.
pointed the fingers in the velocity direction and then thumb in the magnetic force direction.
And your thumb in the magnetic force direction. And the perpendicular to the palm is giving the direction of magnetic field, right?
Yeah.
Yeah, that you can do. Or you can do it from hit and trial method. But for this method, you again have to remember one more formula. Again, a right hand palm rule basically. Or you can do it using right hand thumb rule. That your magnetic field should be perpendicular to both the things. So direction which is perpendicular to both could be either positive z-axis or negative z-axis, right? Because your velocity is along x-axis, your magnetic force is along y-axis. So direction which is perpendicular to both is either positive z, which is outwards, or negative z, which is inwards. Is it clear?
Yes.
Now let's assume that my magnetic field is along positive z-axis, outwards. Apply right-hand thumb rule and get the direction of magnetic force. If I assume that, now I'm using hit and trial method. If I assume that your magnetic field is along positive z-axis, apply right-hand thumb rule and get the direction of magnetic force. Keep your finger along velocity and curl it outwards, out of the plane of the board.
It's coming downwards for me.
Coming downwards. It's coming downwards for which type of particle? Positively charged particle or negatively charged particle?
Positively charged.
But this particle is
Negative. So the opposite.
force would be up. So where should be your magnetic field? It should be outwards or inwards? This must be the correct answer, right?
Yes.
Because if you take inwards, then your force will come downwards. So the rule that you are using, the right hand palm rule, that rule is for positively charged particle. For negatively charged particle, you just have to reverse the direction. Clear?
Yes, sir.
Better to use this thing because you will need this concept in many conceptual problems. You should always remember this thing that magnetic field is perpendicular to both force as well as velocity. So you can decide that it's either along positive z axis or along negative z axis. Then you can apply hit and trial method and you can conclude that this is along positive z axis. So the correct answer is this. Your magnetic field should be along positive z axis. The next is cyclotron. The next application is cyclotron, but this cyclotron is part of deleted syllabus. So I'm skipping this topic. It's not a part of the syllabus for this session. But you should at least know what is cyclotron and what is the use of cyclotron. Cyclotron is a device which is used to accelerate charged particles. For example, say you have a proton plus E. You want to throw this proton at a very high velocity. So to throw this proton at a very high velocity, you need a device which is known as cyclotron. But cyclotron is not a part of syllabus. So I'm not doing this cyclotron, but at least remember this thing, that it is used to accelerate charge.